This video is intended to serve as a review of the sampling design concepts we have talked about. Although this is not a comprehensive review, it will highlight many of the important concepts. We will start with revisiting our definition of a representative sample. When it comes to generating a representative sample, it is not a trivial challenge. By this, I mean a sample that accurately reflects the characteristics you are trying to capture from the population. Because of this, the quality of a sample is as important as the sample size. As we move through the next few weeks of the class, it should become clear that all the designs we talk about are just different ways of selecting which parts of the population to measure, and that this is a critical step. If we were conducting a survey of all voters and we utilize a protocol that systematically excludes voters younger than 30, the sample would be worthless. When it comes to designing a probability-based sampling strategy, there are three requirements we need to meet. As we think through all the considerations necessary to create a sampling design, we have to evaluate if they allow us to meet these requirements. First, do we have some kind of random sample? Without some concept of randomness, you cannot determine the probability of selection and therefore cannot make statistical inference about your population. Do we have a measure of interspersion within the sample? Your sampling units need to capture the variability of the target population. This helps ensure that we have a representative sample being drawn. Generally in natural resource management, we do this by proportionally sampling things along the edge of a population and within the interior of a population to account for any differences in the environment. And finally, we need to ensure that our samples are independent. You need to make sure that your plots are sufficiently spaced apart such that you are not remeasuring the same information or that your samples do not have autocorrelation between them. In natural resources, we generally accomplish this by using what's called sampling without replacement. Our most simplistic probability-based sampling strategy is simple random sampling. Most often, when we talk about selecting sampling units in natural resource management, we are referring to selecting the location of a plot. When we are doing this, we must remember that an underlying assumption of inferential statistics is that any sampling design must ensure a known relative probability of each observation being selected and that the samples will be independent of the other selected units. This is the basis for a random sample. Although very similar, this differs from simple random sampling, which requires us to have a known equal probability for each sampling unit. When it comes down to actually designing a sample, our management objectives should tell us what we want to measure. However, knowing when to stop measuring is much harder and more important to determine. All of the sampling we conduct in natural resources needs to be statistically viable while remaining practical. When it comes to determining when to stop sampling, we have many possible options, including stopping when we have enough plots collected to provide whatever necessary precision we deem we need, or stopping simply because it's becoming inefficient to continue sampling, or stopping because we have answered our question, or because it's just becoming too expensive to continue sampling. Should we sample too much, we will have wasted time and money. If we sample too little, we will have high errors to deal with in our decision-making process. When it comes to our statistical approaches, preliminary data from simple random sampling can provide an estimate of variability and allow us to determine exactly how many plots we will need to achieve a desired precision level. An important aspect to sampling the natural world is considering how our sampling unit will influence how we see the population.
The scale at which we choose to view a population at influences. If we look at the plots now, using 5 1/5 acre plots, we now have samples of 4, 5, 7, 2, and 5 respectively, giving us a mean of 23 trees per acre and a standard deviation of 9.1 trees per acre. While we see almost no change in the sample means, there is a significant decrease in the sample standard deviation at the larger plot size.
The reason this can be an important consideration in sample size determination is that we may want to use one plot size in our sampling design, but may have some preliminary data from another plot size that we need to use in determining our population variability. Although it will only provide a rough way of scaling our plot size, we can use this formula to scale the variance of our original plot size in the preliminary data against the plot size we want to use in our sampling design to get an estimate of variance at the scale we want it at. Now that we are thinking about how we select sampling units, let us look at stratification to see a more efficient way of doing this.
The basic underpinning of stratified random sampling is that we take advantage of prior knowledge about the population to improve our sampling design. Within this system, we seek to improve our precision by optimally allocating our sampling efforts into areas where we have homogeneous values. By taking advantage of our knowledge about the population, we're able to divide the population into strata of expected subpopulations, or strata with a known range of potential values for sampling. When doing this, strata must not overlap, and all areas of interest must be included. In the big picture, the only drawback to stratification is the increased effort needed for the bookkeeping of the data and computation of the statistics.
There are three sample allocation approaches we will look at. The first approach is equal allocation, where the sample size is set equally for each strata. The calculation for this process is fairly simple, where we say that the number of samples in each strata is equal to the total number of availables divided by the number of strata. The second approach to sample allocation is proportional allocation, when the number of plots per strata is proportional to the area of the strata. This process makes the sampling intensity equal for all strata, meaning that we sample the same proportion of area in each strata. The final approach to allocation is called optimal or Nyman allocation, in which the available plots are allocated by an equation that ensures that the standard error is minimized. In this case, the number of plots that a strata receives is proportional to its area-weighted standard deviation. When it comes down to it, though, in natural resource management, there are rarely a need to do anything other than proportional allocation. It has been said that the simplicity and self-weighting feature of proportional allocation are probably worth a 10 to 20% increase in variance. It is important to remember that the allocation process is simply a guide to determining how many samples each strata should receive. We must then use our judgment and determine if this allocation is the best way to meet our sampling requirements. Now let us look at a way of ensuring we obtain a representative sample.
Generally, when we start talking about systematic sampling, there are two reasons we want to. The second main reason we use a systematic sampling approach, particularly in natural resources, is that this approach is very convenient for most field sampling exercises. When used well, this approach can help decrease travel time and also allow field crews to make field observations of the entire population as they move between sample locations. When we look at this in a more strictly statistical sense,
As we increase the number of samples that we take, we see that the simple random sample begins to expand what it represents. But the systematic sampling simply infills areas it did not have good information for. By spanning the range of possible samples with a systematic sample, we should be ensuring we create a representative sample. Now let us look at one of our more advanced methods with double sampling.
If we remember back to week 2, we talked about the difference.
When it comes to double sampling, we have 3 approaches: ratio estimation, regression estimation, and difference estimation to work from. In order to figure out which approach to use, we generally start by plotting the sample XY data pairs and then determining if the points appear linear with an intercept near 0, which would indicate that either ratio or regression estimation should perform well. And if the points appear linear but do not pass near the origin, then regression will outperform ratio estimation. If it appears more than one technique can be used, we should pick the technique that yields the smallest variance for the Y population parameter. This means we need to actually perform the calculations for each technique and compare the results to see which will give us the narrowest confidence interval. Now let us look at our last way of selecting sampling units through cluster sampling.
With that in mind, cluster sampling refers. When it comes to performing cluster sampling designs, we have two.
When it comes to cluster sampling, the first reason we use it is when the frame we place around the population does not allow us to create a good list of sampling units. Cluster sampling might be more feasible since a list of clusters is easier to obtain. The second major reason we use cluster sampling is to lower the cost for the amount of information being collected. This is particularly important when sampling large populations where sampling units might be spaced at greater distances. Generally, in large populations, the distance between sampling units will increase, which will subsequently cost time and money. So cluster sampling is used when the area of the population is very large, meaning that the sampling units are widely dispersed. This can also lead to a waste of time trying to locate sampling units.